Ensuring that model adheres to responsible AI principles was a core focus of this project, particularly regarding fairness, transparency, and accountability. In line with those principles, fairness was assigned using metrics like demographic party difference and mean absolute error disparity. By evaluating these fairness metrics, I aim to ensure that the model's predictions were not biased towards specific demographic groups. Specifically, the sensitive feature under consideration was the neighborhood group, with a focus on the purpose in the Manhattan. The demographic party difference shows that the model's prediction did not favor one group over another, while the mean absolute error display helps identify potential disparities in predictions errors between different groups. This evaluation revolved the disparity of 42.02, which highlight area of potential improvement in reducing bias. To further ensure fairness, strategies such as rebalancing and dataset, applying fairness constraints during the training using adversarial debiasing could be implemented in the future interactions of the model. Addressing bias and fairness in the model was a critical step in this project. To mitigate bias, I focused on assigning how well the model performs according to different groups and ensuring that its predictions did not disparity favors disadvantages any particular group. The model's prediction was evaluating across different features such as neighborhood group and the room type, and fairness check like demographic parity was applied. By assigning these metrics, I ensured that the model was not unfairly biased against a certain neighborhood or property types, fostering more equitable outcomes for all groups. Despite achieving demographic party difference equals to 0, which suggests that the predictions were fairly distributed across the neighborhood groups, further steps could be taken to reduce the disparity of the prediction errors. It's identified by the mean absolute error disparity. Making machine learning models interpretable is essential for the ensuring transparency and supporting the ethical decision making. In this project, I used two key techniques to make the model interpretable: SHAP and LIME model. SHAP values provide insight into contributor of each features to the predicted housing price, make it clear which feature had the most significant impact. For example, neighborhood and longitude were identified as important drivers in predicting the price of the properties. This level of transparency ensured that the model's decisions were understandable and justifiable. By making the model's inner working visible, SHAP supported the easier decision making by allowing stakeholders verifying that model is not relying on the discriminatory and or biased features. Similarly, LIME was used to explain in individual predictions, particularly for specific properties, by approaching the model's behavior locally around this instance. The method helps to understand why certain predictions were made for a specific data point and ensure that the model is behaving constantly across in different groups. By visualizing how model operates and ensuring that it's treated similar inside similarly, LIME support fairness audits and build confidence in the ethical integrity of the model. Through a combination of the fairness check and the model interpretability techniques, I ensure that the model adheres to responsible AI principles supporting transparency, fairness, and accountability. The use of SHAP and LIM has made the model more understandable, ensuring ethical decision making and forecasting trust in the predictions made. With these techniques, stakeholders can verify that model decisions are both equitable and justifiable, leading to a better, more informed decision making in the real world applications.